Welcome to the AI Research Roundup. I'm your host, Alex. Today is May 7th, 2025. We're looking at an ICLR conference paper, Feedback Favors the Generalization of Neural ODEs, published on January 22nd, 2025, so just over 3 months ago. This paper tackles how neural ordinary differential equations, or neural ODEs, which model continuous time dynamics, can struggle to generalize. It proposes a feedback neural network, a novel two-degree of freedom architecture, using a feedback loop to correct learned dynamics in real time. Alright, this first figure nicely illustrates their core idea. On the left, a typical neural ODE, current state xt, feeds into learned dynamics f underscore neural for prediction. But the key is, on the right, their feedback network. It adds a loop using the error between actual and estimated state, processed by either a gain L or another neural net, to correct f underscore neural in real time. Okay, so figure 2 then shows this correction process in action. We see the initial learned dynamics, f underscore neural that's the blue curve, being adjusted over time. At each step, T1, T2, T3, the error between the actual and estimated state, multiplied by a gain L pushes the prediction, the red curve f underscore hat, underscore neural closer to the true underlying dynamics ft This visualizes that real-time adaptation. Building on that real-time adaptation, Figure 3 then shows how they extend this for multi-step prediction. The current state xt goes into the feedback NN, predicting xt plus ts . This output then becomes the input for the next step, and this process repeats, allowing predictions over a longer horizon. They also mention using a gain decay strategy here to help manage noise accumulation over these steps. Okay. Figure 4 then gives us a practical look at this. It shows heat maps of prediction errors for a spiral curve. We see how different feedback gains perform under varying degrees of uncertainty. When gain is 0, it's a standard neural ODE, and errors increase with uncertainty. But with an appropriate feedback gain, the system keeps errors lower. The right panel even zooms in, highlighting that optimal gain region for better performance. Now, Figure 5 gives us a really clear toy example of this linear feedback in action. We see a neural ODE trained on one spiral, panel A, and it learns that fine, as shown in Circa. But when faced with a new test spiral with different underlying dynamics, panel B, the standard neural ODE's performance degrades significantly, which you can see in D. However, their feedback NN, shown in E, adapts much better, leading to smaller prediction errors over multiple steps, as highlighted in F. Alright, Figure 6 then explores how they train their system using domain randomization. That's basically training with lots of varied simulated conditions. Panel A shows that if you train the base neural ODE itself with domain randomization, its performance on the original task actually degrades. So their better approach is in Panel B. Train the base ODE normally, freeze it, then train just the feedback part with domain randomization. Panel C shows this feedback training loss. So to wrap up, the authors convincingly show that adding a feedback loop to neural ordinary differential equations, creating what they call a two-degree of freedom system, significantly boosts generalization. This real-time correction led to impressive results, like better trajectory prediction for irregular objects and robust quadrature control using MPC, or model predictive control, even under substantial uncertainties. Thanks for tuning in to the AI Research Roundup.